When we examine the formation of the early universe, we tend to credit a single element for the result. Standard cosmology operates on a very straightforward assumption. Because hydrogen is the most abundant element, it is universally viewed as the primary architect of the first stars and galaxies. It is the baseline of our standard models. But this split-screen visualization shows a significant discrepancy. On the left is the theoretical prediction model of a universe built primarily by hydrogen. On the right is the actual universe observation data. The two do not align. Traditional hydrogen-based models predict a cosmos filled almost entirely with spiral galaxies. In reality, we observe a high count of elliptical galaxies. These models underestimate star birth rates in small galaxies, and they cannot mathematically account for the scale of supermassive black holes at galactic centers. To resolve these anomalies, Nathaniel Faxon Cherier proposed the Cosmic Helium Evolution Theory, or CHET. This framework reevaluates the baryonic, or ordinary matter, composition of the early universe. CHET identifies that the true driver of early cosmic structure was a highly efficient 7.9% fraction of primordial helium-4. This specific slice of the chemical pie dictated the actual rate of early star formation. This diagram compares the atomic structure of a standard hydrogen-1 atom to primordial helium-4. Hydrogen-1 has a mass of 1 atomic unit and a nuclear binding energy of 2.2 mega-electron-volts per nucleon. Helium-4 is much heavier, with a mass of 4 units, and holds a much higher binding energy of 7.1 mega-electron-volts. Because of its higher mass and thermal conductivity, helium-4 radiates heat efficiently. This allows massive clouds of helium-4 to cool quickly and collapse into dense clusters, while surrounding hydrogen remains diffuse and slow to react. This rapid thermodynamic collapse triggered the birth of the very first stars, just 50 to 100 million years after the Big Bang. Helium-4 bypassed hydrogen entirely to light up the Dark Ages. These early helium-4 stars were massive, ranging from 10 to 90 times the mass of our Sun, burning at blistering blue-white temperatures. And because they burned so efficiently, they lived short lives before collapsing violently in on themselves. The subatomic efficiency of helium-4 gave it a 100 million year head start. It sequenced the massive structural foundations of the universe, while hydrogen clouds were still drifting. When those massive early helium-4 stars died, they immediately collapsed into stellar black holes. These dense remnants acted as the direct seeds for the supermassive black holes we observe today. As these early black holes formed, they continued to feed on the surrounding helium-4 gas. This specific accretion process regulated their rapid growth, solving the mass anomaly that hydrogen models struggle to explain. We can see the direct results in galaxy morphology. This chart maps primordial helium-4 abundance on the x-axis against galaxy mass and type on the y-axis. Regions with high helium-4 abundance correlate exactly with massive elliptical galaxies, while lower abundances yield smaller spiral or irregular galaxies. Standard hydrogen stars didn't begin forming until 100 to 200 million years after the Big Bang. By the time they ignited, they were forced to coalesce within the gravitational parameters already locked in place by the helium-4 black holes. This two-phased evolution produces the incredibly dense, high-energy structures we see at galactic cores. The heavy structural lifting was completed early on. The shapes, types, and center masses of all modern galaxies serve as direct fossil records of a rapid, extreme helium-4 epoch. These 3 core CHET equations govern galaxy formation, star formation, and black hole growth. Notice the variable for helium-4 density, ρHe4, is the central mathematical driver. Run against NASA, Spitzer, and Chandra observational data, these predictions match reality with 97.42 to 99.01% accuracy. Scaling out from individual galaxies, we can look at the largest known architecture, the cosmic web. The universe is crisscrossed by vast filaments of galaxy clusters. Under CHET, these massive structures formed exactly along ancient networks of helium-4 enriched gas. Conversely, the massive cosmic voids exist in the pockets where helium-4 was simply absent. The large-scale distribution of the entire cosmos is a 13.8 billion-year-old map of primordial helium density fluctuations. Next-generation observational instruments are currently tasked with probing the deep universe to gather more data on this framework. Telescopes are targeting high redshift galaxies to measure distinct helium-4 abundance, while massive radio telescope arrays observe ancient star-forming regions to verify the gas density predictions. In his book, My Dear Universe, Cherier outlines a specific structural theorem. The quantum level, the cosmic level, and the physical principles binding them are the exact same process perceived at different scales. The architecture of the largest structures in the cosmos is ultimately dictated by the subatomic properties of a tiny 7.9% fraction of early universe matter.